Okay, February, March 2020, paper 4, variant 2. Question 1. A rocket is launched vertically upwards from the ground. The rocket travels with a uniform acceleration from rest. After 8 seconds, the speed of the rocket is 120 meters per second. Can I find the acceleration? Yes, acceleration would be equal to v minus u over t. The final velocity is 120. Acceleration equals v minus u over t. The final velocity is 120. Initial velocity is 0 because it's moving from rest, and the time is 8 seconds. So what is 120 divided by 8? It is 15 meters per second squared. On figure 1.1, draw the graph for the motion of the rocket in the first 8 seconds. In the first 8 seconds, it was moving with a constant acceleration. This is a speed time graph. So we need to draw a straight line, starting off with 0 and 0. After 8 seconds, this is 8. So this is 8. Let's zoom in a bit. Okay, it reached a speed of 120. Where is 120? It's above the 100. 4 squares above 100. 4 squares above 100. So at this point, we need to draw a straight line. Using a ruler, you can draw a straight line. Okay, good enough. Now, use the graph to determine the height of the rocket. Can I find the height of the rocket? Yes. Basically, the distance traveled, which is the area under the graph. What is the area under the graph? Half times base times height. So half times 8 times 120. What is half times 8 times 120? It is 480 meters. From time 8 seconds to 20 seconds, the rocket rises with increasing speed but decreasing acceleration. From 8 to 20. From 20 to 25, it is moving with a constant speed less than 200 meters per second. So first of all, we need to draw the increasing speed and decreasing acceleration part. It will be a curve, right? Decreasing acceleration, it would be a curve. So something like this, right? And then from 20 to 25, it was moving with a constant speed, less than 200. Constant speed less than 200. Okay, increasing speed, decreasing acceleration, it would curve towards the x-axis. Figure 2.1 shows an athlete crossing the finishing line. As she crosses the finishing line, her speed is 10 meters per second. She slows down to 4 meters per second. The mass of the athlete is 71 kilograms. Can I find the impulse? Yes, impulse is the change in momentum. Change in momentum. So basically mv minus mu. mv minus mu. 71 times 10 minus 71 times 4. What is the change in momentum? It would be 400. Let's calculate it. 71 times, yes, 426. 426 newtons dot second. Can I use kilograms dot meter per second? Yes, you can. Define impulse in terms of force and time. Impulse equals force times time. The athlete takes 1.2 seconds to slow down from a speed of 10 to 4. Can I find the resultant force? Yes, I can. So impulse equals force times time. To find the force, it would be impulse over time. Basically, 426 divided by the time, which is 1.2. It is 355 newtons. 355 newtons. Calculate the force required to give a mass of 71 kilograms and acceleration of 6.4. Force equals mass times acceleration. So 71 times 6.4. What is 71 times 6.4? Yes, 454 newtons. 454 newtons. Okay. Question 3. Figure 3.1 shows a model of a wind turbine used to demonstrate the use of wind energy to generate electricity. The mass of air passing through the circular area is 7.5 kilograms each second. The kinetic energy is 240 joules. Can I find the speed of the air? Yes, I can find the speed of the air. If you have the kinetic energy equals half mv squared. Kinetic energy equals half m. To find the velocity or to find the speed, basically you will say it is 2 times the kinetic energy. Yes, 2 times kinetic energy over mass square root. Okay, but square root. So basically it is square root 2 times 240 joules over the mass, which would be, what's square root 2 times 240 over 7.5. The speed would be yes, 8 meters per second. Kinetic energy of the air drives the generator. State the input power. What is the input power? Power equals energy over time. Energy over time. What is the energy? It's the kinetic energy. 240. What is the time taken? Each second. So 1 second. Basically, it's 240 watts. The output current of the generator is 2 amperes. The potential difference is 11 volts. Can I find the output power? Power equals IV or VI. 2 times 11, 22 watts. Right? Can I find the efficiency? Yes, I can find the efficiency in percentage. So basically, efficiency is the useful output over the total input. The useful output is 22 and the total input was 240. Multiply by 100 to find the efficiency. 22 divided by, which is 9.16 or 9.2%. 9.2%. The density of air is 1.3 kilograms per meter cube. Can I find the volume? Yes, I can find the volume passing each second. Density equals mass over volume. So volume equals mass over density. The mass is 7.3. 7.5 divided by 1.3. What is 7.5 divided by 1.3? This is 5.76 or 5.8 meters cubed. 5.8 meters cubed. Specific latent heat, this is cancelled. This part of the question is cancelled. We can only solve part I. We can only find the specific heat capacity. Specific heat capacity, C equals energy over M delta T of the water. So what is the energy supplied? The water loses, or the energy lost, is 35,000 joules. 35,000 joules. The mass of the water is 0.35 kilograms, and the change in temperature, the initial temperature of the water was 24.5 degrees Celsius. The temperature of the water decreases to 0 degrees Celsius. So basically 24.5 minus 0. 0.5 minus 0. Can I find the C of the water? Yes. 35,000 divided by 0.35 times 24.5. 4,081 or 4,082. 4,082. What is the unit? Do not forget about the unit. Joules per kilogram degree Celsius. Okay. II is cancelled because it has to do with the latent heat of the ice. Complete the sentences with words that describe the main process of thermal energy transferred in each case. A man goes for a walk on a cold day. He touches a metal gate which removes thermal energy from his hands by, if he's touching the gate, it's by conduction. Yes, by conduction. He holds the side of a cup containing a hot drink. His hands gain thermal energy by, yes, again by conduction. Okay, by conduction. Some farm workers lit a fire. The man warms his hand by the side of the fire. He didn't say above the fire, he said by the side of the fire. So if you're standing by the side of the fire, you will get warmed up by radiation. By radiation. Described in terms of particles that transfer hmm, of thermal energy through the metal of the gate after transfer from the man's hand. Basically inside the gate through the particles. How does the energy get transferred by the free moving electrons? Okay, free moving electrons and lattice vibration. You can say both. You have the free, okay, moving electrons and lattice vibration of molecules. Figure 5.1 shows a car on a sunny day in a hot country. The object labeled A, this one, okay, the object A is placed inside the windscreen. It is used by the owner of the car to reduce the temperature rise inside the car. Ring the most suitable material for the outer surface of object A. Explain your choice. Should it be dull black, dull white, shiny black? Which? Hmm. Yes, it should be shiny white. Why should it be shiny white? Hmm. Why should it be shiny white? Because shiny white is the best reflector of infrared radiation. Best reflector. Can I say that it's also the worst absorber? Yes, you can say so. Best reflector and worst absorber of what? Of infrared radiation. Okay, figure 6.1 shows crests of a water wave moving from left to right. On figure 6.1, draw three more crests to the right of A. This is diffraction. Okay, I solved part II. Yes, this is diffraction. What's happening in this diffraction? Okay, this is diffraction. The waves will start to spread. You need to put three more points. So let's measure the distance between these two crests. I'll add a point here, another point here, and another point here. Basically, three equal distances. They have to be equal distances. And then I'll draw a line which will start to curve at the end. Okay, another line, and it will start to curve at the end. And another one. Okay. The first part of the line you need to draw it using a ruler, and then the curve using your hands. This is diffraction. Yes, 6.2 shows the crests of another wave moving from left to right in a different part of the harbor, moving from deep to shallow, moving from deep to shallow. Can I state the name before drawing? Yes, I can state the name. This is refraction, right? This is refraction. How can I draw the wave? How can I draw the wave of this refraction? Yes, the wave has to be perpendicular. The wave has to be perpendicular um, to these crests, which is moving in this direction. You have to make sure that this wave, this direction, this arrow is perpendicular. It has refracted in this direction. Okay. Complete table 6.1 to state whether each of these properties has increased, decreased, or stayed the same as it passes into the shallow water. As the water waves pass into the shallow water, what happens to the wavelength? Decrease. Frequency stays the same. We know that the frequency will not change. What about the speed? It also decreases. Why? Because the speed and the wavelength are always together. If you increase the wavelength, the speed increases and vice versa. Figure 7.1 shows a converging lens and image I formed when an object is placed to the left of the lens. So the object is now placed to the left of the lens. The principal focuses are A and B. So A and B are principal focuses. On figure 7.1, draw two rays to locate the position of the object. This is a rather easy drawing. Why would it be easy? Because you can you can, okay, if I'm talking about this drawing, only this drawing, you can assume that this image is the object. You can assume that this image is the object, and then start to draw the rays from the image, emerging from the image. Definitely, we know that they are not emerging from the image, okay? But you can assume. Why? Because this is a real image. Because this is a real image. If it was a virtual image, the drawing would have been a bit different. Okay, would have been a bit more different. But again, this is a real image, so you can assume that the rays are emerging from the image, even though we know that the rays are not being generated. They're not produced from the image. They're actually from the object. Let's draw. First line, can I draw the easy line, which moves parallel to the principal axis? Okay, you have to draw this line parallel to the principal axis. Again, you're drawing using your ruler until it reaches the center of the lens, and then it will pass through the focal point. Okay, passes through the focal point and continue the line a bit further up. Right, this is the first line. The second line passes through the center of the lens, right, through the center of the lens. Okay, from the tip of the image. Okay, from the tip of the image all the way to the tip of the object. Again, you're drawing using a ruler. Okay, they might meet at this point, so this is your object. This is object O. Okay, bring all of the following distances that are equal to the focal length of this lens. Focal length AB, no. AC, yes. AC. CB, yes. CB is also a focal length. Figure 7.2 shows green light passing through a triangular glass block. Red light enters the triangular block along the same path. Can I draw the red light? Yes. How can I draw the red light? We know that they are Roy Gibbs, right? Roy Gibbs. And this is a prism, so the red will be drawn right above the green, just above the green. So inside the prism, we'll draw the red above the green a bit. Okay, and outside the prism, it will also be above the green. So this is the red. If it were blue, indigo, violet, it would have been below the green. Figure 7.2, we have the path of red light. Okay, we drew the path of the red light. On figure 7.3, again, we have the green light passing through a rectangular glass block. Red light enters the rectangular block shown in figure 7.3. Draw the path of the light within the rectangular glass block, and then after it leaves the glass block. Can I draw the red light inside and out of the glass block? Yes, I can do that. I can do that. Again, Roy Gibev. Roy, R means that it would be refracted less. Okay? It would be refracted less. And then, as it moves away, yes, it will refract, or it will have the same angle of refraction. How can I draw it less? If you think about it, it would almost be the same, but just to prove it, to you, you have the normal line, right? You have the normal line. What do I mean by being refracted less? So, for example, the angle of refraction of the green is whatever, 30 degrees, right? 30 degrees. Refracted less meaning that it would have a larger angle of refraction. It would be refracted, it is bent less. So the red light would be just above the green light this way. And then as it emerges, as it moves away, it will move this way, almost parallel to the green light. I cannot draw a parallel line somehow. Again, you're drawing using a ruler, so please. Okay, so this is parallel. Let's assume that this is parallel, okay? Anyway, you do not need to draw the normal line or the angle of refraction or anything. Okay, moving on. Figure 8.1 shows a circuit. The lamp has a resistance of 3 ohms. Line XY represents a uniform resistance wire of 6 ohms. So this wire has a length of 2 meters. It has a total resistance of 6 ohms. Can I find the reading on the ammeter? Can I find the current? Yes, I equals what? I equals V over R, right? I equals V over R. The voltage is 12 volts. What is the total resistance? What is the total resistance? 3 plus 2 plus 6, right? The total resistance is 3 plus 2 plus 6. Why? Because they are all in series. So 12 over 3 plus 2 plus 6, or over 11. 12, what's 12 over 11? 12 divided by 11 is 1.0909, 1.1 amperes, right? 1.1 amps. So far, so good. In figure 8.2. Now, some things have changed in this figure. What has changed? We added a 1.5 ohm resistor parallel to this resistance wire, right? But this resistance wire isn't at full length now. It's not at full length. It's only at a length of 0.6 meters, right? The sliding contact has moved. The sliding contact has moved. Therefore, the total resistance has it decreased or increased? The sliding contact has moved, the length has decreased, therefore the resistance will also, yes, it will also decrease. Can I find the new resistance of this wire from X to Q? Yes, I can find it from X to Q. The total resistance was what? The total resistance was 6 ohms when the total length was 2 meters. If the length is now 0.6 meters, can I find the new resistance? Yes, cross multiply. So 6 times 0.6 divided by 2, it would be 1.8. So this is the new, resistance of the wire, 1.8 ohms. Good. Now, you have 1.8 and 1.5. They are parallel. How can I find the combined resistance of these parallel resistors? Product over sum. 1.8 times 1.5 over 1.8 plus 1.5. Product over sum. 1.8 times 1.5 over 1.8 plus 1.5, which is 0.81. 0.8 or 0.81 ohms, right? These are the parallel resistors. What would the total resistance be? Can I just add the other resistors? Yes, you can add the other resistors. Why? Because they are in series. They are in series with this block. So 2 plus 3 plus 0.81. 2 plus 3 plus, which is 5.81 ohms. 5.81 ohms. Question 9 is cancelled. Okay, all of question 9 is cancelled. Question 10. You have a simplified top view of a flat coil. There is an alternating current in the coil. Describe the magnetic field of this alternating current. Can I describe the magnetic field? Yes, I can. What would happen to this magnetic field? It would be a magnetic field, an alternating magnetic field, right? An alternating magnetic field would be created around the wire, right? An alternating magnetic field. Magnetic field will be created or will be produced due to the alternating current or the changing current. State what quantity is induced in the base of the pan. What quantity is induced? This is the base of the pan. it's made of steel, due to this alternating current. So you might say that there is, yes, an EMF is induced, right? It's as if you're thinking about a transformer, for example, when you have an alternating current that cuts the secondary coil, inducing what? Inducing an alternating EMF. Okay, inducing an alternating EMF or voltage. The pan contains water. State and explain the effect of the quantity induced in part B on the temperature of the water in the pan. So this EMF, this voltage, what would it do to the temperature of the water? The temperature would increase. Yes. Why would the temperature increase? Because of the EMF, which creates what? The EMF passing, the voltage. If you have voltage, then you will have a current. If you have a voltage, then you will have a current. So this current increases the temperature. Okay, it increases the temperature by increasing the amount of kinetic energy and heat energy in the pan. Okay, what happens? What happens to the temperature? Temperature increases. Temperature increases. Why does it increase? Okay, due to the current passed, okay, or created in the base of the pan, which increases the heat energy and kinetic energy, which increases, okay, the kinetic energy and, okay, let me write down, and heat energy. Okay. The isotope hydrogen 1 has a proton number of 1 and nucleon number of 1. Proton number of 1, nucleon number of 1. Two isotopes of helium 3 and helium 4. Helium 3 has a proton number of 2, nucleon number of 3. Helium 4 has a nucleon number of 4. Okay. Complete the table. Can I complete the table? Yes, this is easy. How many neutrons are there in helium 3? If helium 3 has a proton number of 2, nucleon number of 3, so it has 2 protons, therefore it has only 1 neutron. What about helium 4? It has also 2 protons. It has, why? Because it's helium. So it has 2 protons. Therefore, it would have 2 neutrons. Number of electrons, it would be equal to the number of protons in both. Number of protons, so 2 and 2. Mass compared to a neutral atom of hydrogen 1. The mass of it compared. What is the mass of helium 3? What is the mass of helium 4? The helium 3, the mass of it would be 3. The helium 4, the mass of it would be 4. But that's it. That's it. An experiment takes place in a laboratory shielded from all background radiation. Okay. A sample of radioactive material is wrapped in aluminum foil of thickness 0.1 millimeters. A detector of ionizing radiation placed 1 centimeter from the foil records a reading. From the aluminum foil, it records a reading. A piece of aluminum of thickness 5 millimeters is placed between the detector and the foil. The reading, or the detector reading, drops to 0. State and explain any type of radiation passing through the aluminum foil. So first of all, you had a thin aluminum foil and then you added a thick aluminum foil. When you had this thin aluminum foil, it gave off a reading. The detector could detect some ionizing radiation, and then when you added the thick aluminum foil, it couldn't detect any radiation, right? So what type of radiation is this? It's beta, and only beta. Beta and only beta. Why? Because it can pass through thin foil. Okay, so let's write it down. Beta. Okay. Why? Because it can pass through thin foil, but not thick foil, right? Why can't it be alpha or gamma? Alpha would be stopped either way, right? And gamma would be detected either way, right? Okay.